Okay. Well, hello there, good people. Today we are talking about projectile motion. Now, when we talk about projectile motion, the first thing, of course, is to talk about what a projectile is. A projectile is an object that gets launched into free fall. You've seen projectile motion happen all the time. Anytime that you throw something, you're seeing projectile motion because you're launching that object into a fall. For example, if you throw a football, you see that football follows a nice little parabolic path. Anytime you turn on the sprinklers outside, you see that those sprinklers also go in a very nice arch. Now, there is a reason that all projectile motion, anything that you launch into free fall, always follows a nice arch of motion. And we're going to discuss that a little bit today, and we're also going to talk about mathematically how to analyze a projectile motion problem. Oh, wow. Well, hello. Did you see that? Or was that just me? I hope I'm not crazy. Okay, let's go ahead and take a look. Maybe this is not going to work. We're having a little bit of a panicky moment here, folks. Let me adjust my computer really quick once. Okay, well, I didn't really find much of an issue, so I think we're just going to keep on cranking along here, and we'll see how this goes. Okay. Whoa, let's talk a little bit about projectile motion here. Suppose that I were to launch something off of a cliff, something like a muffin. If I were to launch a muffin off a cliff, not, of course, because I disrespect muffins, but because perhaps I had a friend who I needed to throw the muffin to. If I were to launch a muffin off a cliff, I want to talk a little bit about what would happen with that muffin. Well, first, we can agree. This muffin, if I throw it straight off the cliff like this, pretend that's a straight line. If I throw it straight off the cliff like this muffin would experience a nice curve like this. Now, the first thing that we need to acknowledge about projectile motion is that in projectile motion, the object moves in both the x direction and in the y direction. Both are true. And here's the second thing about projectile motion that we have to acknowledge, is that in projectile motion, the x direction and the y direction operate independently. They are completely independent of each other. And what we mean by that is what happens in the x direction does not impact what happens in the y direction. And what happens in the y direction does not impact what happens in the x direction. So, let's take a little look here. Whenever we look at a projectile motion problem, we're always going to separate out this motion into x direction motion and y direction motion. Okay. Oh my, that's an embarrassing line. Let's try again. Okay, great. Now first, I want to start by talking conceptually about what happens in the x direction and what happens in the y direction. Let's start with the y direction. As this muffin falls, can you picture its motion in just the y direction? Obviously, in the x direction, it's moving forward, but could you picture the motion of this muffin in just the y direction if we were ignoring the x direction, if we weren't thinking about it at all? If we were ignoring the fact that the muffin is moving forward, you would see that this muffin is basically just falling in the y direction. In the y direction, it's undergoing free fall. Just like anything else that gets dropped, it's accelerating down towards the earth, getting faster and faster and faster as it falls. That's what's happening in the y direction. In the x direction, this muffin is moving forward. Now, I want you to imagine this in your brain. Imagine it without the y direction. Without the y direction, without any of the downward fall, all you would see is that this muffin is moving forward. Now, this is the part of the program where I ask my students, I say, okay, students, so in the x direction, as this little muffin is moving, once it has left my hand and is now flying out, is there anything that is speeding up the muffin in the x direction? And students say no. Once it leaves your hand, there's nothing speeding it up in the x direction. And I say, okay, students, once it leaves my hand, is there anything that is slowing it down in the x direction? And students will typically give mixed responses here. Some people say no, and other people say yes. And the people who say yes say air resistance is slowing it down. That is true that air resistance will slow the muffin down. But for this class, we are going to ignore the effects of air resistance in projectile motion problems. There are two reasons for this. First, because if you do take into account the effects of air resistance in projectile motion problems, this problem gets really, really complicated really, really fast. So that is one reason why we will ignore it. But the second reason is because we did already ignore air resistance in the y direction. We said that this little muffin is in free fall, which means it has no outside forces, nothing except for gravity. It is under the influence of nothing but gravity. So there is no air resistance that we say is impacting this muffin in the y direction. It would be unfair of us to say there's no air resistance in the y direction, but there is air resistance in the x direction. So what we say is ignoring air resistance. There is nothing that is making it go faster forward, and there's nothing that's slowing it down forward. So we say that in the x direction, we have constant motion. It's a combination of constant motion in the x direction and free fall in the y direction that always creates this nice and beautiful parabolic arc. It's falling, but it's also moving forward as it falls. And it's getting faster and faster and faster in the y direction as it falls. So it starts out nice and flat here because it's not moving that fast in the y direction. So it starts out as a line. But then as gravity starts to accelerate it, it starts to get faster and faster and faster in the y direction until here towards the end it's much steeper in the y direction and it's accomplishing much less in the x direction. Not because it's slowed down in the x direction, but just because it's moving so much faster in the y direction. This is why you see this nice little parabolic arc all the time for any projectile motion, is it's a combination of that constant motion in the x direction with that free fall in the y direction. Okay. Now let's take a look here. We're going to try a little bit of a practice problem. Suppose that I told you that you had a muffin and that you were going to throw the muffin off the edge of a cliff. Now suppose that you knew that the muffin had, come on, we got it. Here we go. That the height of the cliff that the muffin is on is 200 meters. That is a pretty large cliff. And now suppose that you know that you can throw a muffin with an initial velocity in the x direction of, let's say, something reasonable like 10 meters per second. That's pretty fast. That's not too bad. Now, let's say I ask you, how far away from the cliff is this muffin going to land? Okay, here's how we would start this problem. The first thing that you would do is you would draw a picture like this. When you draw a picture like this, next you have to define the x and y direction, and you have to define which ways you want to be positive. Now, I'm going to say that this way is positive x because the muffin is moving in that direction. And then, and here's a part that kind of freaks students out, so just hold your breath here. You're going to be okay. What I'm going to choose for my y direction is I am going to say, for this example, that the muffin is going down and that it's speeding up down. So the acceleration is down and its displacement is also going to be down. So I'm going to say that down is positive y. Now oftentimes students freak out here because they say, Miss Wilson, that is not how Mr. Saxon taught me. No, Mr. Saxon taught me that, sorry, for some reason my pen is not writing. They say, Mr. Saxon taught me that the positive x direction is always this way, to the right. And they said, I always learned that the positive y-axis is always up, and this violates Mr. Saxon's good principles. But here's a secret, students. In physics class, you get to decide which way you want to call positive and negative based on what makes sense to you. So if you would like to violate Mr. Saxon's ways, then you are more than welcome to. If, however, you say, no, Mr. Saxon is my guide and he has brought me thus far, and John Saxon would be disappointed in me, I totally understand. Some students see this and they become very uncomfortable. If you would like to say that positive is up then you are also welcome to say positive y is in the up direction. It's whatever works best for you. I'm going to show you, though, how to do it with positive y in the negative direction, and then we'll do another example with positive y in the positive direction. Or in the up direction. Sorry, excuse me. Wow, that was contradictory. Okay, here we go. Here's what I'm thinking. First, I'm looking for how far I'm going to go in the x direction. I've already written all my knowns and unknowns on my picture, so I don't need to rewrite them anywhere, but you do need to create a t-chart where you divide up the x direction and the y direction because we are going to analyze them separately since they operate independently. In the x direction, I'm looking for delta x, so I'm going to start by saying this. Because I have constant motion, my initial velocity in the x direction, which is 10 meters per second, positive, that is always going to be my velocity in the x direction. And so because it's always going to be my velocity in the x direction, it's also going to be the same as my average velocity in the x direction. If I'm going the same speed the whole time, then that is my average. So it's also going to be my average velocity in the x direction. And I know an equation for v average. I can say that v average is equal to delta x over delta t. And that shows constant motion in the x direction. Now, let's rearrange to solve for what we're looking for. We are looking for delta x. And we say, I'm thinking if I want to find delta x, how far away it lands here, then I can use v average in the x direction times delta t. Here's the problem though. I know my v average in the x direction because it's my v initial in the x direction, and I know I threw this muffin at 10 meters per second, but I do not know my time. This is where we will use the y direction. The x direction and the y direction are completely independent of each other except for one variable, and that one variable is time. Time unites the x direction and the y direction because when this muffin falls, the time at which this muffin stops in the y direction is also the time at which it stops in the x direction. So the total amount of time that it is moving for is going to be the same in both the x direction and the y direction. That's why time is the variable that unites both. So I'm going to look in the y direction to find my time. And that's why I'm going to move this little guy over here. Okay, let's look in the y direction to find our time. To look in the y direction, here's what I'm looking for. I'm looking for a delta t. Now, you don't need to rewrite all of your knowns and unknowns over here. I am going to do it so that I can kind of help you figure out what equation we're going to use. But in general, you don't have to rewrite them all over here. I'm looking for a delta t because once I find a delta t, then I can use it for my delta x. I'm looking for a delta t. I know that my delta y is going to be positive 200 meters. And I say it's going to be positive 200 meters because I said that down is positive and this little muffin is moving down. Then I know that my acceleration in the y direction, I know that guy as well. In the y direction, my acceleration is going to be g. It's going to be positive 9.81 meters per second squared. Notice the positive sign here because, again, I'm accelerating down and I call down positive. And then there's one more secret given that I have that's a little bit of a sneaky one. I know my initial velocity in the y direction is 0. The reason why I know my initial velocity in the y direction is 0 is because this muffin got thrown horizontally. It didn't start by heading up towards the sky, and it didn't start by plummeting down towards the ground, though eventually it will be plummeting down towards the ground. It started by just moving horizontally. So my initial velocity in the y direction is 0 because it didn't start with any y direction motion. Now I look at these variables, I say I'm looking for a delta t, I have a delta y, which is a displacement, I have an acceleration, and I have an initial speed in the y direction, and I check my bag of tricks and I say which of my equations will be best suited for the job. Did you say this equation? Yeah, fantastic. By the way, you definitely, most definitely do have to have all of these equations memorized so that when you see these variables like this, the first thing that pops into your head is delta y is equal to v initial delta t plus 1/2 a delta t squared. Now, normally this is a delta x, but I call it a delta y here because I'm dealing with a delta y. And normally this is just a v initial, but I call it a v initial y because I'm looking at the v initial in the y direction in particular. And I can also call this an ay here as well. Okay, now remember, my goal is to find delta t. Once I have delta t, I can use it to find delta x. Let's rearrange to solve for delta t. The first thing that I do is I say, hey, this whole term is going to go away because my initial velocity in the y direction is 0. So this whole term is going to become 0. Now I can rearrange and solve for delta t. When I do, I have that delta t is equal to multiply both sides by 2, so 2 delta y, divide both sides by the acceleration in the y direction, divided by ay. Oh, there's a bell. And then we got a squared here, take the square root of both sides, like so. And there's my equation for delta t. Now you know that every square root sign comes with a secret plus or minus symbol that lives out front. We do have a plus or minus symbol here, but you are quite intelligent and you know, Ms. Wilson, I'm never, ever, ever going to be dealing with a negative time here. So you don't actually have to show me that plus or minus sign. I will just assume that you will not be using a negative time and that you'll always be using the positive time. You can also write this, if you would like, as, oh gosh, I'm really going to have to cram it in here. Okay, as 2 delta y, sorry, we're really squishy in there, 2 delta y all over g, because isn't the acceleration in the y direction equal to g? This is the part where I ask students, can we plug in numbers now? And some students are like, yes, and I'm like, no, don't do it, because delta t is not my end game. My end game is delta x. That's what I'm solving for. So what I'm not going to do is I'm not going to plug in numbers here and get a value for time. What I am going to do is I am going to plug in an algebraic expression in for delta t here, and then I'll plug in numbers. So I write this as v average in the x direction times my delta t, which is the square root of 2 delta y all over g, like this. And now I'm good to plug in numbers. When I plug in numbers, I plug in 10.0, oh gosh, I'm going to run out of space here. 10.0, please ignore the way that I'm squishing everything together, meters per second times the square root of 2 times positive 200 meters divided by g, which is going to be positive 9.81 meters per second squared. Plug that into your calculators and see what you get. When I do it, because I haven't done this problem yet before, since I just made up these numbers, let's see what happens. For my delta x, I get 60, let's see, how many sixes do I need? 3? Okay, 63.9 meters. I include as well a positive sign here to indicate my displacement is positive. Okay, perfecto. That is an example projectile motion problem, and this would be all the work that you would show. You'd start with a picture with all your knowns and unknowns labeled. You'd start with the axes over here. You'd divide it up into your x direction and your y direction. You'd show all the work in the x direction, all the work in the y direction. Rearrange algebraically to solve for time, plug it back into the x direction. Then you can plug in numbers, and then you get to a final answer. Okay. We're now going to try another practice problem, but before we do try another practice problem, I wanted to talk a little bit conceptually real quick here. One moment, please, as I get this to load up here. Here's a question for you. Suppose that I had, okay, well, I guess brown will work fine. Suppose that I had 2 bullets, and one of these bullets I put into a gun. And then suppose that I launched this bullet out of the gun. Suppose that at the same time that I was launching this bullet, I had in my other hand another bullet. I'll draw it like right back behind the first bullet. Suppose that I have in my hand another bullet. And what I'm going to do is as I launch this first bullet out of the gun, I'm also going to at the same time drop this second bullet that I'm holding in my hand. Here's the question. Which bullet will hit the ground first? The one that I shot out of the gun or the one that I dropped with my hand? The correct answer is both bullets would hit the ground at the same time. Here's why. In projectile motion, the X direction and the Y direction operate independently of each other. So what happens in the X direction doesn't impact what happens in the Y direction. When I ask you the question, which one will hit the ground first, I'm asking which one will travel this amount of Y first. Both the bullet that I drop and the bullet that comes out of the gun, both of those bullets have the same amount of work to do in the Y direction. They both start at the same height and they both end at the floor. And so because they both have the same job to do in the Y direction, it's going to take them the exact same amount of time to do it. And so the bullet from the gun will hit the ground at the same time as the bullet that I drop. Even though the bullet from my gun has an initial velocity in the X direction, that doesn't impact how long it takes for that bullet to hit the ground. It just impacts where it will land. So the bullet from the gun will hit the ground much further away, but they'll both hit the ground at the same time. This, of course, relies on the idea that I am firing this bullet perfectly horizontally straight. If instead I took this gun and I aimed it up towards the sky and then I shot off this bullet, well then the bullet that I drop and the bullet that I shoot, they wouldn't have the same job to do in the Y direction because the bullet that I drop just has to go straight down. But the bullet that I shoot upwards has to go up to the top of its path, make it to the top, and then make it down to the ground. And so it has a much longer job, and so that one would take much longer to get to the ground. But the main idea is if they have the same job to do in the Y direction, doesn't matter what's happening in the X direction, it'll take them the same amount of time to do it. Okay, let's go ahead and look at another practice problem. A new drawing. Here we go. Okay. Suppose this time that now I have a cliff, and this time I'm going to launch a muffin off the cliff, and let's say that I launch this muffin, because I've been training and I've been getting better, now I can launch muffins with an initial speed of 15 meters per second. So let's say that I launch it going that fast. Someone on the ground sees the muffin land a distance of 7 meters away from the base of the cliff. Here is a question for you. Is if this were to happen, could you figure out how tall the cliff is? You say, well, yeah, for sure, Ms. Wilson. That would be no problem. First thing that I would do is I would make a picture, very similar to the one that you've done here. Then I want to find my axes. Let's say this time that up is positive y for all of you Saxon people, and that to the right is positive x. And now let's divide this up into the x direction and the y direction. In the x direction, we have constant motion, which means my initial velocity in the x direction will equal my velocity in the x direction all the time, which will be my average velocity in the x direction. So that is most certainly true. Because I have a delta v average in the x direction here, I can call this is going to equal my delta x over my delta t. In the y direction, I have free fall, so I can use the equation delta y is equal to v initial in the y direction delta t plus 1/2 a delta t squared. And this is my a in the y direction. Now here's a secret for you students. Are you ready? In this class, you can always, really, literally, you can always use this equation in your x direction every time, and you can always use this equation in the y direction every single time. What you will do every single time is you will start on either one side or the other. You'll start with this equation, and then you'll pull from the other equation and solve for time, and then you'll plug it in. That's what you'll do almost every single time. Let's take a look at this example. In this example, I'm looking for delta y. So I'm looking at delta y is equal to all of this stuff. Now my initial velocity in the y direction is 0, so that cancels out. I'm left with 1/2 times a, but that acceleration is g, so I'm going to call it g. 1/2 g delta t squared. Now here's what I know. I'm looking for delta y. I know g, but I don't have delta t. So this time I'm going to go to the x direction to find it. To find it, I start by saying, okay, let's do some rearranging work. My delta t is going to equal my delta x divided by my v average in the x direction, which we know is the same as my initial velocity in the x direction. Now that I have an algebraic expression here, I can plug that expression back over into my y side equation. When I plug it in, I get that delta y is equal to 1/2 times g, and then plug in my delta t, delta x over v average in the x direction. But wait, my time is squared, so I need to square this little value here. Now I have the height of the cliff in terms of things that I've been given. G, which I know, delta x, which is the distance away that the muffin lands, and my initial velocity in the x direction, which we know is 15 meters per second. This is where I can plug in numbers. When I plug in numbers, I plug in 1/2 times. This time, my g is negative because I said that up was positive. So negative 9.81 meters per second squared times my displacement is going to be positive, don't forget your signs over there, positive 7.00 meters divided by, once again, don't forget your signs, positive 1.50 meters per second. All of that gets squared. Go ahead and type it into your calculator. I don't know it yet because I just came up with these numbers just now. Okay. And I got a very small cliff. Like, I'm wondering if I did this right. But I think that I did. Yeah? Okay. I got 1.0. We got 3 sig figs here. 1.07 meters. That is a cute little cliff. Adorable. Don't forget that we do need positives and negatives here. My negative 9.81 meters per second squared here makes this a negative 1.07 meters. Now here's going to be kind of a weird thing. If I asked you for how tall the cliff is, you would just say it's 1.07 meters tall. That is not, so I'm trying to undo, okay, there. That is not a distance, this is not a displacement, it's just literally how tall the cliff is. But if I asked you how far the muffin went, then you need to say the muffin went negative 1.07 meters for its displacement. So there's kind of like a weird funky thing about like distance and displacement and that kind of thing. But yeah, there you go, there's that problem. We'll do one last problem today and then we will call it a day. Let's get a new drawing going. Here's our last example for today. Suppose that this time you had a muffin on top of a cliff. And you know that the distance away is, let's try making something up here, 25.0 meters. And you want to land that muffin on a target that is 25.0 meters away. And we'll call it the positive x direction. Do define your positives and negatives, of course. This time I'm going to call down positive, and I'm going to call to the right positive x. Here is my little muffin. Bing, 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 bing. Okay, here's my little muffin. Say that I know that the height of my cliff is, let's go with, sorry, I'm thinking, 22.0 meters. And you want to know how fast do you have to throw this muffin in order for it to land on the target? Do you agree that if you throw it, where'd my equal sign go? If you throw it not fast enough, it'll go and it'll land here because it doesn't have enough speed in the x direction. If you throw it too fast, it'll go and you'll stretch out that parabola and it'll make it way further in the x direction before it hits the ground. If you do it at just the right amount, though, it'll go and it'll land right here on your target. Let's go ahead and see exactly, wow, that is not what I wanted. Let's go ahead and see exactly how fast we would need to launch this guy. Okay. Once I draw a picture where I've established all my knowns and unknowns, then I write my x and y direction separated out. Here's my x direction, and here is my y direction. Okay. In the x direction, I start by saying I'm looking for the initial velocity in the x direction, and I know that that's going to equal the average velocity in the x direction. And I know that that's going to equal a delta x over a delta t. I have a delta x problem though, I don't have a delta t, so I go over to my y direction to find it. I'm always going to use the equation delta y is equal to v initial y delta t plus 1/2 a delta t squared. This is my acceleration in the y direction. I do include my vector hats if they're appropriate here. And then I already know that this guy's going to cancel out, so that makes my job very easy because it starts with no initial velocity in the y direction. And now my job is to rearrange and solve for t. To rearrange and solve for t, I start by saying that I have delta y is equal to 1/2 times g times delta t squared, and let's rearrange. I'm going to multiply both sides by 2. I'm going to divide both sides by g. And then finally, I'm going to take the square root of both sides in order to get that time all by its lonesome. Okay, now I take this guy right here and I am going to plug him back into this equation. So I get that v average, which is my initial velocity in the x direction. My average velocity in the x direction is equal to delta x divided by the square root of 2 delta y over g. Now some kids feel great about just plugging this into their calculators, but some other kids are like, no, I do not like it. I definitely do not like this setup here because I got a fraction and another fraction, and I don't like doubly fractions. If you'd like to do a little more algebraic rearranging, you're more than welcome to. You can just take this little guy who's down here in the second fraction and you can shove him up on the top here. So you get delta x is times, the square root of g over 2 delta y. If you like that step, great, use it. If you don't like that step, great, don't use it. Then we can plug in numbers here, and I'm kind of running out of space just a wee bit here, so I'm gonna work to the side, but you would really never work to the side, you would always work vertically. Okay, let's plug in numbers here. For G, we plug in positive, because the way that I define my directions, positive 9.81 meters per second squared. For my, I need signs over here. For my, oh gosh, wait, guys, I forgot my X. How could you let me do this? Ah. Okay, we'll plug it in here really tiny. It's positive 25.0 meters. Oh gosh, that's so awkward and embarrassing. I hope you can even still consider reading that. Okay. Sorry. Then for my delta y, it's positive 22.0 meters because of the way that I define my positives and negatives. Plug it into your calculator here. We get 25 times the square root of 9.81 divided by, second set of parentheses here, 2 times 22. And then I get, then I need to throw this muffin with an initial speed of 11.8 meters per second in the positive x direction, which, considering my muffin throwing training, I would say that's totally doable for us. Okay, and that's all for today, folks. You can see that generally with these problems, you set up a diagram, you label your knowns and unknowns on your diagram, you label your axes as positive and negative, you divide it up into the x direction and the y direction. You always start with the same equation in the x direction and same equation in the y direction, but then you're going to rearrange one of the sides to find time, plug in that rearranged algebraic expression for time into the other side, then plug in numbers to get to your final answer. Okay, good people. I hope that you have a wonderful, wonderful rest of your day, and I'll see you all next time. Bye, good people.